In our last lesson, we reorganized our building blocks chart according to an atom's connectedness rather than by the number of electron pair domains it has. There are two reasons why we do this. One is that an atom's connectedness is usually fixed and rarely changes. The other reason is that we have an experimental technique known as X-ray crystallography that will allow us to determine an atom's connectedness. There are two distinct limitations of X-ray crystallography, however. The first of which is that it cannot detect hydrogen atoms, since hydrogen is such a small atom and has the lowest atomic mass number of all of the elements in the periodic table. The second limitation is that it cannot detect multiple bonds or the electron configuration about each atom. X-ray crystallography makes up for these two limitations in a huge way by providing the Cartesian coordinates of every non-hydrogen atom. With these coordinates, we are able to measure the exact distance between two specific atoms, as well as the bond angles between a set of three atoms. With this advantage in place, we are able to deduce the Lewis structure of nearly any organic compound. What you can see below is the connectivity map, or the X-ray structure, of CH5N3. Based on its molecular formula, we could see that this compound is neutral. And based off of the X-ray structure provided, you could see that the distances between each carbon and nitrogen atom is given as well. Now we can't see the hydrogen atoms, nor can we see whether a bond is a single or double bond. Based off of these distances, we should be able to deduce the Lewis structure of this molecule. What you should do now is to pause this video and try to draw the Lewis structure for CH5N3 on your own, using the information that is provided here. Okay, here we go. While the given bond distances between each atom is enough to deduce the Lewis structure for this compound, what you will notice if I rotate this molecule is that each of the atoms lie in the same plane. If I were to measure the bond angle between the nitrogen and carbon atoms in any of these cases, what I can notice is that I get a bond angle of 120 degrees, which indicates trigonoplanar geometry. And what I can notice if I look at the bond lengths for each carbon and nitrogen bond is that two of the bonds are relatively the same and slightly longer than the bond that is indicated as 1.28 angstroms. If we were to now attempt drawing the Lewis structure for this compound, we could begin by drawing the backbone that we see in the X-ray structure, meaning we would draw a carbon atom that is bound to three nitrogen atoms. From our X-ray structure, we saw that one of these carbon and nitrogen bonds was shorter than the other two, thus indicating that one of the carbon and nitrogen bonds is either a double or triple bond. Since carbon is a second row element and can never exceed a full octet of electrons, we know that the shorter bond seen in the X-ray structure has to be a double bond, because if it was a triple bond, the carbon atom would have 10 valence electrons. Now if we were to try to assign each of the 5 remaining hydrogen atoms, we could look at our molecular formula and see that this compound is neutral. If we assign 2 hydrogen atoms to the 2 nitrogen atoms that have single bonds to the carbon atom, and 1 hydrogen atom to the nitrogen that has a double bond to the carbon atom, based on our rules of formal charge, we could see that each of these nitrogen atoms would be neutral as well, and the compound provided here would match both the X-ray structure and the neutral molecular formula that was given to us.